Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to today's training. This is video number 2 of the training series. We're going to do this one today on atmospheric energy. And if you look at this particular image on the title slide, you'll notice that when we talk about energy in the atmosphere, we need to talk about not only the atmosphere, but also the oceans. There's a lot of energy involved there, as well as with earthquakes and plate tectonics and a lot of different things going on in the atmosphere all the way down to the outer core of the Earth. There's a lot of atmospheric energy. But today we're going to really apply this introduction to atmospheric energy to the weather that we see every day. The first thing I want to start off with in today's training is a brief description of what's known as atmospheric physics. Now, you may have had a course of physics before, whether it be in high school or college. When we talk about physics as it applies to physical meteorology, this deals with a combination of dynamic and thermodynamic processes that account for the existence of numerous atmospheric conditions. And to understand the weather elements that we experience every day and analyze these meteorological conditions, one must know how to apply the fundamental principles of physics. Look at the graphic there in the lower right on this slide, and you'll notice there's a lot of motion exchange of energy as well. When we talk about the atmospheric physics, whether we're talking about a cloud in its developmental stages or dissipating stages, whether that cloud is actually producing any kind of precipitation. We look at the ocean surface as well as the land surface, the different flow over mountainous or higher elevated terrain as well as what we went over last time. We talked about the incoming shortwave solar radiation as well as outgoing long-wave Earth radiation. So there's a lot of atmospheric physics within the atmosphere itself and a lot of energy and motion. Now, what exactly, when we talk about in physics, what are we going to talk about when it comes to motion? In physics, the laws of motion state that an object at rest never starts to move by itself. A push or a pull must be exerted on it by some other object or external force. So I want you to think about this. It's early in the morning, you're getting up for school or for work, and when you're in bed there, you really don't want to move a whole lot, and you won't move. Maybe somebody pushes you out of bed. That's going to change the fact that your body was once at rest, but now if somebody pushes you out of bed, that results in the motion. The atmosphere has complex motions not only in the vertical on a hot summer day, but also in the horizontal planes. The key terms associated with motion that we're going to go over include what's known as inertia, speed, direction, velocity, and acceleration. The bottom right graphic or image there shows the motion that goes on in the atmosphere. And we need to think of the atmosphere as three-dimensional, from the surface to higher up, well above the ground level. And there's a lot of motions going on, whether those be up motions or rising air motion, ascending air, those blue arrows with the arrow pointing up, or downward or descending air motion, which is indicated by the blue arrows pointing down. And you'll have areas of what's known as convergence, where the air comes together at the surface. That air then ascends, and then it spreads apart wide above that area of low level coming together or convergence of air. And then you may have coming together air convergence at the higher elevations, and then just sinking, descending air through a depth of the atmosphere. And once the air reaches the surface, it spreads out or diverges. So there's a lot of up and down motion. There's horizontal motion as well, as far as advection in the atmosphere. So there's a lot of motion going on. When you see the wind blowing trees, that is a form of motion. The wind is creating motion of other objects. So what are some of these key motion terms? I'll just do a brief description on these. The first one is known as inertia. Inertia basically means an object at rest never moves unless something or someone moves it. This is a property of all forms of matter. And when we talk about matter, specifically applying to the atmosphere and the weather, we talk about solid forms of matter, liquid forms of matter, or gaseous forms of matter. Now, again, that kind of goes back to the example I used to kick things off, where if you're laying in bed in the morning, it takes sometimes a lot of energy. It feels like a lot of energy just to get up out of bed, right? You're just kind of dragging there, the alarm goes off, or maybe you're one of those people that pushes the alarm multiple times for the snooze button. Resist any change in its state of rest, and that would definitely describe human beings in the morning, if you're not a morning person anyway, or any state of motion. Speed, on the other hand, is the rate at which something moves in a given amount of time. If the rate of movement of a hurricane, let's say, is 15 knots or 12 miles per hour, we say that it has speed. All we're mentioning is the magnitude at which it's moving. Direction is the line along which something moves or lies. In weather, we speak of direction as either toward or the direction from which an object is moving. For example, in weather, when we say we have a north wind or northerly wind, we're saying the winds are coming from the north. Moving on to velocity. With velocity, this is going to describe both the rate at which a body moves and the direction in which it is traveling. So this is an indicator of both speed and direction. When I say velocity, that implies both are involved. So now we use that hurricane example again. If a hurricane with its speed, forward speed of 15 knots per hour, and it's moving westward, now I'm attaching a direction westward with the magnitude or speed of movement. So that now has a velocity, has both a rate and a direction of movement. And you'll see that commonly when, especially during hurricane season, when you see the meteorologists on TV talking about, where is a particular tropical cyclone headed. They'll have both a direction and then speed associated with that. So that's the velocity. And then acceleration. This applies to a rate of change of the speed and or the velocity of matter with time. So if a hurricane is presently moving at 15 knots, and then let's say it moves 18 knots 1 hour from now, and then at 21 knots 2 hours from now, it is said to be accelerating at a rate of 3 knots per hour. And there's a lot of atmospheric influences that tend to speed up the movement, for example, of a hurricane. So just wanted to show you that acceleration. If you apply it to everyday life, it's getting in your car. It's pushing down the gas pedal. Maybe you give a little more force with your foot on the gas pedal, the accelerator, and that causes you to pick up speed or accelerate. All right, so moving on to the laws of motion. And this is something many of you probably have already experienced through your education. But I thought it would be a good time to again mention these. The laws of motion definitely apply to weather. Newton's first law of motion is known as the law of inertia, which states every body continues in its state of rest or uniform motion traveling in a straight line unless it is compelled to change by applied forces. For example, if I were to roll a ball across a table, it would roll in a straight line unless somebody that was standing maybe further down along the side of the table actually redirected the ball and actually pushed on the ball and directed it to a different direction. So overall, with Newton's first law of motion and law of inertia, there would be no movement of great quantities of air unless there were forces that caused the movement. So again, getting back to our weather example, air tends to move from higher toward lower pressure. That's something known as a pressure gradient, or change of pressure over distance between two pressure systems. And so Newton's first law of motion applies as far as moving that great quantity of air. Now, Newton's second law of motion states the change of motion of a body is proportional to the applied force and takes place in the direction of the straight line in which that force is applied. A change of motion in the atmosphere is determined by the force acting upon it, and there's many forces that act upon, if I were to simply describe it as an air parcel moving in the atmosphere, that change takes place in the direction of the applied force. And then finally, Newton's third law of motion. This is very important in any form in the atmosphere. To every action, there is an always opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal and directed to contrary parts. So one big thing about the atmosphere, just like in nature in general, nature or the atmosphere always tries to seek a point of equilibrium or balance. When things are temporarily out of balance, the atmosphere is working harder to restore that balance. And so bottom line is, if I were to use an upper level weather chart, for example, and if I said there was this big ridge in the western United States with higher heights, what goes up must come down. There must be an equal and opposite reaction to that. So if I have a very strongly amplified upper level ridge that's going all the way in the western U.S. up into western Canada, then I have to have a downstream trough to counteract the up and down motion. Moving on now to discussion on work and energy. Now, work is done when a force succeeds in overcoming a body's inertia and moving the body in the direction the force is applied. So work is basically equal to the force times the distance. Now, the amount of work done is the product of the magnitude of the force and the distance moved. So simply put, we factor in force and distance, force times distance, and that gives us the amount of work done. Energy, on the other hand, is defined as the ability to do work. And one big thing about energy is it can be neither created nor destroyed. It just simply changes its form. Or it relocates. Now, there are two types of energy that are very important to weather. These are potential and kinetic energy. Potential energy is the amount of energy that may be available to a body due to its position. This is primarily due to gravity. The higher the body is, the greater is the potential. Kinetic energy, on the other hand, is the energy of motion. Now, if you look at the diagram at the top, that little image there at the top of the girl. Initially, she's standing up on a higher elevation. Let's say she's standing at the top of a building, in the example in the upper right-hand corner. She's got a red ball. She is just standing there. She puts the ball over the edge of the building. That ball has potential energy right at that point because it's a elevated distance above the ground below. So let's say she's on the 10th floor of a building, on the roof of the 10th floor of a building. She extends her arms out, puts the ball over the edge of that top of the building. That ball, at that point in time, there's potential energy there. Now, once she releases the ball, that potential energy is going to transfer into energy of motion, known as kinetic energy. Now, the higher you lift something above the ground, the greater the potential energy. And that, again, is mainly due to the force of gravity, as gravity acts downward on all falling objects at 9.8 meters per second squared. So, again, the higher you lift something above, the greater the potential energy will be converted to kinetic energy. And not only that, but the greater the potential for that object to do work. So, for example, if you were to hold a brick high above, let's say above your head, and you were to drop that brick and it were to land on your foot, that brick would go from potential energy to kinetic energy, and once that brick landed on your foot, it would be doing work on your foot. And you would feel that in the form of pain, right? So the total amount of energy a body possesses is the sum of its potential and kinetic energy. So both of those combined. Again, the more energy available, the greater the amount of work done. Moving on to the next discussion, a topic on force. Now, there are two types of forces that exist. There's contact force, and there's what's known as action at a distant force. Now, contact force is the force that occurs when pressure is put on an object directly through physical contact. So it makes sense, contact force, right? For example, if you were to have, let's say, a rubber ball or something inflatable, let's say a beach ball, that makes it better and easier to demonstrate. So if you had a beach ball and let's say you put your hand and push down on the top of that beach ball, that is contact force. You are directly in contact with the top of that beach ball and you're exerting force downward on it. Another example would be what I show here. Your hand is the force your hand exerts when you push your coffee cup across the table. Action at a distant force, on the other hand, is a force that acts through empty space without contact. And an example of this would be gravity. Nobody's really touching gravity to force it, right? It's just a natural occurrence in the atmosphere that acts downward. States of matter. Now we're really taking this energy concept and we're going to tie it into what are known as the states of matter. We're going to get into phase changes from solid liquids and gases. But first, let's describe what matter is and how the solids, liquids, and gases are defined. So matter is basically anything that occupies space and has weight. Bottom line, anything that takes up space and has weight, that's considered matter. States of matter, the state of matter is very important in meteorology. The three states include solid, liquid, and gas. And what's so unique about water is it can exist in all three states simultaneously at the same time. Now, solids are substances that have a definite volume and a shape and retain their original shape and volume after being moved from one container to another. An example of a solid in this case would be a block of wood. If I were to take a block of wood and move it from one, let's say I move it from a wagon and I throw it in the back of a pickup truck, that block of wood is still going to maintain its same volume. That volume's not going to change. It's the same size, right? And it's going to maintain its same shape. So if I were to throw that block of wood in the back of a truck, it's going to retain the original shape and volume after being moved. Liquids, on the other hand, have a definite volume, and I want you to think about this. Any of the drinks you drink, whether it be a gallon of milk or whether it be sweet tea in one of those big plastic containers, liquids definitely have that definite volume because it's impossible to put them into a smaller space. So you can't take a container of milk and try to pour it in something like really small. If you did, then the volume would remain the same, right? But it would probably spill out of that smaller cup or whatever you're doing. Now, when a liquid is moved from one container to another, it retains its original volume, but takes on the shape of the container. So if I were to take that, let's say I pour milk out of that milk carton, that gallon of milk, the container, and I pour it into an empty 2-liter bottle of soda, it's going to take on the shape of the 2-liter bottle of soda. And then finally, there's gas. Gases have neither a definite shape nor a definite volume. Gases not only take the shape of the container into which they are placed, but they expand and fill it no matter what the volume of the container. For changes of state, now these are very important for sensible weather. Did you know that during certain changes of state, heat is released to the surrounding air? And other phases or changes of state, that heat is absorbed. And so this is very important to our sensible weather. Changes of state are phases. Phase changes of a substance describes a change from a solid to a liquid in the process of melting, a liquid to a vapor in the process of evaporation, a vapor back to a liquid in the form of condensation, and then a liquid to a solid in the form of freezing, solid to a vapor or vapor to a solid in the form of what's known as sublimation. And I'll show you the chart on this in a few slides. Now, water is present in the atmosphere in any or all of these three states and changes back and forth from one state to another. Solid state of water is typically in the form of ice or ice crystals. Have you ever looked up at the sky and saw some very high streaming clouds, really wispy looking clouds? Those are those cirrus clouds well above 20,000 feet above the ground. That is an example of ice crystal clouds, and that would be an example of the solid state of water. The liquid state of water is in the form of raindrops, could be in the form of clouds, as well as fog. And the vapor state or gaseous state of water is in the form of unseen or invisible gases, in the form of water vapor. Now, heat. Heat energy and phase changes. Very important concept in weather. Energy is involved in the various changes of state, or those phase changes that occur in the atmosphere. Each of the changes of state either use heat from the atmosphere, or they release heat into the atmosphere. The heat used by a substance in changing its state is referred to as the latent heat, and is usually stated in calories. Literally, latent means hidden heat. You don't see it. And that heat energy used in changing a state or a phase, for example, from a solid to a liquid, liquid to a solid, that heat is not felt by a thermometer. Okay? All that heat energy is used in breaking down those molecules from a solid ice to a liquid, for example. A calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. That's a definition of a calorie. And so when I talk about heat calories, or the amount of heat energy required to change the phases, or phase changes of any substance in the atmosphere, any form of water, we talk about calories. Now, if I were to go from a solid to a liquid changeover, so solid in the form of ice over to liquid, let's say, like a puddle you'd see. This is fusion, is the change of state from a solid to a liquid at the same temperature. Now, the number of gram calories of heat necessary to change 1 gram of a substance from the solid phase to the liquid phase is known as latent heat of fusion. So to change 1 gram of ice, let's say, to 1 gram of water at a constant temperature and pressure, that requires roughly 80 calories of heat. The phase change from a solid to a liquid, that's going to require heat from the surrounding air, which makes sense, right? If I have a solid ice block, in order for it to melt, let's say the sun comes up and the sun's energy and the radiation heats this block of ice, the solid block of ice. It's absorbing the heat to break down the rigid structure of the molecules within the ice block. So solid to a liquid phase in the form of melting takes in a lot of heat to get the job done. If I go from liquid to solid, on the other hand, the opposite of fusion, by the way, is known as freezing, and this is when a liquid changes into a solid. So in the process of freezing, let's say when you woke up in the morning, there's puddles on the road, right? Throughout the day, the temperatures drop, and those puddles freeze into ice. So just think about this now. So in the act of freezing, the heat is released to the surrounding air. It's given up by the water so it can cool down. So since it requires 80 calories to change 1 gram of ice to 1 gram of water, the same amount of heat is released into the air when 1 gram of water is changed to ice. So whether we're talking solid to a liquid, this is a process known as fusion, or liquid to a solid, which is freezing, both of those phase changes require 80 calories of heat. Now, if I were to go from a liquid to a gas, now water is going to undergo a process that's known as evaporation when changing from a liquid to a gas. The motion of the molecules in the liquid is restricted by the weight of the atmosphere, or more precisely by the atmospheric pressure itself. If the speed of these liquid molecules is sufficiently high, they escape from the surface of the liquid into the atmosphere. It's called evaporation, and they become an invisible gaseous water vapor. Now, as the temperature of the liquid is increased, the speed of the molecules also is increased, and the rate at which the molecules escape from the surface increases as well. So I like to always think about the boiling water on the stove analogy, right? So let's say you put your burner on high, right? You heat a pot of water, put your burner in the highest setting it can be, we're adding a lot of heat to that pot of water, right? as the water continues to heat, eventually the molecules speed up to the point to where you'll see steam coming out of the pan, especially if you put a lid on the pan, right? If you're heating a pan of water, you have a lid on it, and then you take the lid off. After a while, you're going to notice steam, that invisible water vapor coming off the surface of the water because it's boiling. Now, the higher the setting on the stove I turn that, as far as heating the pan of water, the quicker, the more rapid the molecule motion, the more easily it is for those water molecules to escape the water surface and become that gaseous vapor, that steam you see. So during evaporation, heat is actually absorbed. And it's quite a bit of heat calories required for this conversion from a liquid to a gas. It requires 597 heat calories to change things. So that's quite a few compared to when we're talking about solid to liquid was 80 calories of heat, liquid to solid 80 calories of heat. We need 597 calories of heat to change things over from a liquid to that gas. What about gas to a liquid? This process, when we go from an invisible gas or water vapor back to a liquid, this is known as condensation. And it's the opposite of evaporation because water vapor undergoes a change of state from a gas back to a liquid. And take a look at the billowing clouds in the upper right-hand corner of the slide. That right there is a visible reminder of the process of condensation. In order for these clouds to form, these big, tall, puffy cumulus clouds, the surface of the Earth is heated, the air rises, and as that air rises, it cools. And sooner or later, that invisible water vapor that's in the air will convert back over into the form of liquid droplets and form these clouds. Now, when condensation occurs, it's really important, and I'll get to that here in a minute. Now, a condition of saturation must exist before condensation can occur. In other words, the air must contain all the water vapor it can hold at that temperature before any of it can condense from the atmosphere. Now, heat energy is released during condensation. So when we go from a gas and convert over to a liquid water, there's a lot of heat energy that's released to the surrounding air. Now, this is very important for thunderstorm development in the atmosphere, tall, billowing thunderstorm clouds, as well as for growing instability within a developing tropical cyclone. So this is a very important process when we go from a gas to a liquid in the atmosphere and we form clouds, and then that process of condensation releases heat to the surrounding air and things continue to billow up. Now, solid to a gas or a gas to a solid. Sublimation is the change of state from the solid directly to a vapor, or vice versa, from a vapor to a solid at the same temperature. Look at how many heat calories it takes for sublimation to occur. So, one thing I should mention about this is sublimation is a phase change which occurs when a solid goes directly to a gas, or a gas to a solid, and it bypasses the liquid state. It doesn't even, so in other words, if I were to go from a solid to a gas, I'm not going to go from solid to liquid to the gas. I'm going to go directly from a solid to the gas. So we're completely skipping the liquid stage. And this requires 677.3 heat calories. So this, out of all phase changes in the atmosphere, all the phase changes of water, this one requires the greatest amount of heat calories. Here's a great diagram to show you everything we just talked about. And so, let me see here. The best way to explain this again is if you, for example, you look at the top diagram there, you have freezing from water to ice. We're showing you that. We're showing you from a water vapor to water through condensation. And then we're showing a water vapor basically going back to water again. So in general, what we're doing is freezing, condensation, they release heat to the surrounding air. That's what we're showing you in the top diagram. And there's the values that we talked about. 80 heat calories to go from water to ice and ice to water. And then from a water vapor or a gas to water via condensation or evaporation requires 597 heat calories. If I go to the bottom, look what happens in the bottom. Sublimation, I'm going from a water vapor directly to a solid, ice, or back again. So a lot of things going on here. We have a lot of energy exchanges occurring, even during phase changes of water right around us every day. And these phase changes, and whether they release heat to the surrounding air or absorb heat from the surrounding air, are very, very important for the atmosphere and the actual weather we see on a daily basis. Right, so for atmospheric energy, there are two types again. We briefly introduced this at the beginning of the training today. There's kinetic energy and potential energy. Now, according to the kinetic theory of gases, the temperature of gas is dependent on the rate at which molecules are moving about and is proportional to the kinetic energy of those moving molecules. This is what's known as kinetic theory of gases. So, basically, to break this down, the hotter or the more faster moving molecules within a substance, the higher the temperature. The slower moving molecules indicate a colder temperature. Now, an increase in temperature is accompanied by an increase in the internal energy of a gas. And an increase in the internal energy is equal to an increase in the temperature of that gas. So now we're getting into the relationship between internal energy as well as temperature. That relationship between the heat and energy itself is something we call thermodynamics. So if I were to show you the first law of thermodynamics, what does this mean? This law states that the quantity of energy supplied to any system in the form of heat is equal to the work done by the system plus the change in internal energy of the system. There are two main forms of energy involved: internal energy and work energy. Now, internal energy is manifested as sensible heat or simply the temperature, whereas work energy is manifested as pressure changes in a gas. So heat is, bottom line, when we talk about the first law of thermodynamics and why it's so important, is heat is a form of energy. And heat energy cannot be created or destroyed, but again, this is the conservation of energy concept. That energy just simply transfers to another location or changes form entirely. All right, that wraps up the training today on energy and motion. We talked about kinetic energy. I hope you enjoyed the video. We talked about the different types of energy, both energy and motion, kinetic energy, potential energy. We talked about the phase changes of different water, whether we're talking about a solid, a liquid, or a gas, and whether the heat is absorbed or released in those processes. We talked about matter, and we talked about the definition of solids, liquids, and gases, as well as force, work and energy, the laws of motion that Sir Isaac Newton created, and then different key motion terms. Also identified motion, which we have a lot of in the atmosphere, a lot of up and down motion and sideways, horizontal motion. And that wraps things up. Going back to the ending slide here, just want to again remind everybody where to find us on social media. Spot on Weather. We are on Facebook, we are on Instagram, we are on Twitter, and we do have the Spot on Weather Weebly site. Check out the website. I'm telling you, you will not be disappointed if you really love weather. It's a great website. Really don't do a whole lot of posting on Instagram. That's kind of our tertiary social media platform. You will see updated forecasts daily on the Facebook page, the Twitter page, as well as our website, the Spot on Weather Weebly site. We do the 7-day outlook. We have so much cool stuff on the website. Photo galleries, weather archives, weather research, weather training. You name it, we got you covered. Thank you so much for listening in to training topic 2 today on energy and motion. I hope you enjoyed it. Now we'll tie in these concepts as we move along throughout the summer. We're going to tie in these concepts that you're learning today about, potential energy, kinetic energy, as far as the first law of thermodynamics about energy conservation. Think about the first law of thermodynamics, by the way, as if energy cannot be created or destroyed, it can simply change location. We go back to what I talked about with radiation and the uneven heating of the Earth in the first training topic last week, where the equator is heated much more intensely than the polar areas. And so You have the same amount of energy basically in the atmosphere. It's just redistributed accordingly. All right. Thank you so much for watching, everybody. Thank you so much for subscribing to this YouTube channel. Take care, everybody. I wish everybody a good weekend. Stay safe out there.